Hello to my talk AGL at Reutlingen University, Research and Education. My name is Thomas Walzer. I'm Research Associate at Reutlingen University, a university in the south of Germany. I worked on the topics of automotive since my bachelor thesis in the year 2013, and there I developed a concept for a Java OSGI-based IB system based on services and applications for our driving simulation. Therefore, I also defined the CAN messages and the structure of the CAN bus network we are using for the driving simulator. The agenda for today is first I want to introduce you to automotive at Reutlingen University. Then I will show you the past projects, the outgoing work, and possible collaborations. Automotive at Reutlingen University is based in 3 different schools at university: in the School of Computer Science with the Future Mobility Lab, where we are doing the AGL work, with the Cognitive Systems Research Group. They are working, for example, on detection of pedestrians and prediction of their intentions. The second school is the School of Engineering. There are courses in mechatronics, and they are, for example, transform a buggy in an e-buggy, or work on CAN hardware and stuff like this. The third school is the School of Textile and Design, and they have courses in transportation and interior design, and they are doing new interior designs and future mobility concepts. At the moment we are having a look in how we could interdisciplinary work from a concept to a prototype with these 3 faculties. The Future Mobility Lab is the home of our driving simulators and the spot where we are working on AGL. We are developing applications and services for AGL. We are building prototypes that the students could test their software on AGL hardware. And we are working on sensor and actuator systems based on Arduino microcontrollers and on Sapphire. We are focusing on the HTML5 apps because the students are learning this in their courses in the bachelor. And we are developing new concepts, building interior user interfaces, developing services and application. Everything started with the PhD thesis by Emre Yay. He developed an adaptive assistant for safe and energy efficient driving, C-Drive. The assistant learns the driver behavior on the data we get from the car, so shifting, RPMs and the speed, and the system then generating, for example, informations for the right shift moment, and the system will give that audiovisual to the driver. If the driver is not hearing on the signals, for example for shifting, the system will learn that and then never will give a shift message again to the driver. If there is a safety issue, the system will give that messages to the driver. And it was the development of our first driving simulator. C-Drive was the initial build of the driving simulator, so we have a CAN hardware gateway there with 2 ports. We using the driving simulation OpenDS, and we had a gateway software that sent data from OpenDS to the CAN bus and backwards. And there was a PC system for the driver assistants. OpenDS is a free open source developed driving simulation from the German Center for Artificial Intelligence, and it has the possibilities to stream car data over TCP or get values over TCP. So you can send, for example, steering wheel angles from a sensor, or you can send the virtual RPMs or speed from the driving simulation to the CAN bus. It had also OpenDrive support, and on that URL you can find the software. That was the first driving simulator. It was made from wood, and the focus was on the information from the driving simulator and the control of the driving simulation. You can see next to the steering wheel, in front of the steering wheel, there is a display for the IC system, and right next to the steering wheel you can see a little monitor. There the user is getting information from the driving assistance system. Every part you can see here is the input and output part of the driving simulation, and we have a bit more hardware in the back end. Here you see two impressions of that, and on the right side you can see that there are 3 additional monitors, so you can see what the driver is seeing, or you can get the values from the CAN bus on there. And in the right corner you can see the monitor that is giving the information to the driver from the driver assistance. After the PhD thesis, we worked on Mufade. Mufade is a research project with a university in Egypt, in Cairo, and the goal was to develop a low-cost drowsiness system for detection drowsiness and as a plug-in system for trucks, because there are a lot of accidents with trucks in Egypt. We are using for this vital signals, and the device could be attached to the CAN bus and give the drowsiness factor to the driving simulation, or AGL. The next project we did was S-Park. S-Park stands for Smart Parking, and there was the idea to develop a parking management system. We have a lot of parking lots at the university, but a lot of students that came with the cars, so we don't have that much free parking lots at many days. For example, after 9 o'clock it's really hard to get a parking lot, and the students want to reduce the searching time. So the first idea was, how to see which parking lot's free or not. And for that we worked on a detection for parking lots. And this is a sensor system that is based on LoRa and a distance sensor. And if there are other possibilities to get free parking lots, maybe a vision system, I could do that in a cloud with a sensor fusion. And they have an app on the smartphone to see which parking lots are free. The second part of that project was ride sharing. The idea was to reduce the used parking lots by making ride shares, and for that we're working on the topic analyzing the drives from the students and then find, based on time and the routes we are having, ride shares. So this app should be on AGL as well as on the smartphone. On the smartphone you can register new rides and you can join new rides. In AGL, in the car, there was an app that was developed where you can register. So if you join a ride, you can scan a QR code and then say, I'm in the car, and you can say, now I'm leaving the car. And with that system there should be rewards for drivers and passengers. The next project was in interactive bio-based surfaces. We have there a collaboration with the School of Textile and Design and working on smart textiles, functional textiles in the car. At the end we worked on a capacitive sensor that could be an interaction button in the car. And for that we had a button on demand concept that I will show later. So there are 3 options or options groups, and then we have 12 buttons, and all of these 12 buttons have a different option in the different option groups. What we made In the what we made while the project was this. So you see we have an LED matrix in the right upper corner that is under a material that let the LEDs shine a bit through. So there's a good space to change the ambient light of the car, or to give information to the driver or passenger. You see on the left side, there we have a steering wheel, and it's not in the picture, but there are also real pedals to control the driving simulation. On the steering wheel there is a steering wheel angle. And you see the blue dots next to the steering wheel under the display in the middle console. There are our smart Textile buttons. So every blue light indicates that there is a function you could press. And we added a joystick as well to control the shifting. Okay, and for the concept for the buttons on demand, you see here the ID. We have in the bottom the option groups, and there you can choose from blue, it's climate, green, it's multimedia, and orange settings. If you press the green button for multimedia, in the second stage, just the lights for that, so just the green symbols will be shown, and you could choose from that functions. For example, the second button is play pause. If you press on this, the sound or the system will stop and start the multimedia application for that multimedia for that moment. If you, for example, press the volume level button, in the display there will be the option for you to change that. So that will activate AGL, or the possibility in AGL to change that. And if you choose, for example, options, all the orange LEDs will go on, and you see just that information. So if you choose a first option group, you will got the possibility to change that options. Here you see different pictures from the driving simulator. So in the middle we use a Textile that could be equipped with our smart Textiles buttons. The technical part of InBio was to build up the cockpit. It's called Sitzkiste, so it's the driver and the co-driver or passenger. The system is built up that we could change the positions of the drivers, for example, or modify the spaces in that system. We have a board voltage from 13.8 volt, and we have a CAN connection through serial cable and custom Y-CAN adapter that we just could plug in microcontroller CAN-based systems and work. And we have two connections from the cockpit to everything else. It's LAN for the connection between our software to send data to the driving simulation, and a power plug to get power on all the system. So we are independent from the driving simulation and from the audio-visual feedback, because we just could use the driving simulation and send the data from there to our system, or we could have a beamer, a cave, or just a monitor for the visualization part. The current projects starting with, that's the possibilities the students have at the Future Mobility Lab. We have the lecture Human-Machine Interaction, where they learn to build HTML5 apps, and they could use that experience to bring it in the driving simulator. We have elective lectures where the students could do 1 or 2 semesters and do their projects in the laboratory. We have the possibility to do thesis, the master and bachelor thesis in the lab. You could do a master project, which is over 2 semesters. In the first semester we are working on the concept, and in the second semester we will do the implementation. and you could do student jobs at the lab. Here you see an overview over the topics we are working at the moment. So on the left side you see OpenDS, and for that we are working currently on a tool that generates maps for the driving simulation. So you choose a part in a map and then you could drive on that place. OpenDS is sending the data from the car, RPM and speed, to PySim to CAN, and from there it's going to the CAN bus. And PySim to CAN has the possibility to get values from the CAN bus and send that as car control signals to the driving simulation, for example the steering wheel angle. And in PySim to CAN we are working with CAN databases, so we define CAN databases with our messages that we need, and we could use that in PySim to CAN. We can use the same CAN database and put it in our CAN pipeline, and the CAN pipeline will generate everything that you could use the CAN messages in AGL, for example in the IVY system. AGL is connected with the cloud for us, and in the cloud there's the connection to the parking lot service for that system, and in the step before there's the sensor fusion and the parking lot sensor. Here you can see an overview over the CAN bus or CAN bus gateways we have, and we have 6 of them. The first is the powertrain. At the powertrain we have virtual values like the values from motor, RPM, speed, and we have real hardware, the shifting signals. In the chassis we have at the moment the steering wheel and the pedals where we put values in the CAN bus, and in the body we have from the driving simulation a virtual distance sensor. The telematics gateway is for the connection between the IVY and instrument cluster with the whole CAN bus. And in the interior CAN bus we have the climate or the interaction points. It should also be possible to control the seat on that CAN bus. And at least we have the diagnostic CAN bus gateway for OBD. What we are doing on the CAN side, it's the CAN pipeline. It's a current work we are doing in the AGL EG connectivity, and there we develop a pipeline where we can define CAN messages and use them in the AGL service. That is a tool we want to have for the students, that we easily can create new CAN devices and then make them on Arduino, define the CAN messages and then use them in 10 minutes in AGL. And for that we have software that defines CAN messages, and then we build the CAN database. We export that database and can use it with an import by Python in the software, for example PySim to CAN or different softwares. The second time we use the exported database is to convert that database to a JSON file. That JSON file we convert to an AGL CAN plugin, and with that plugin we build an AGL CAN service. What we also did was adding cannelloni to AGL to have CAN over UDP. I will come later to that to show you why we need it. And then the current state of the driving simulator, we are working currently on the upsquares hardware and using one for IVY and one for IC. We have a serial CAN USB adapter for both systems, and we have for the IVY system a radio module and touchscreen and the Unisense system. An additional system we used, you can see on the right side, it's a mobile development station or the station for presentations. The next part, what we did was the map generation. It is a bachelor thesis that was finished 2 or 3 weeks ago, and there was the idea to generate 3D maps from an OpenStreetMap box. So you are going to OpenStreetMap, searching for a part you want to drive, and then you could use our pipeline for the map generation and use it in the driving simulation. The base system was developed now, and now we want to extend it and improve the software, and maybe get a collaboration with the DFKI for that. Here you can see the examples out of that. In the bottom you can see the part in OpenStreetMap, and in the top picture you can see what the first system generates out of that. So you can drive on the streets, and the streets are looking really good for the pipeline. Okay, now we came to the master project, and where we have one group that is working on navigation. So we are developing an Agl Html5 Navigation App for our driving simulation environment. You see in the step before we created the environment for the driving simulation, and now we want to navigate in that. And for that, one student is working on algorithm and a service for that. One is working on the UI for the IV system. One student is having a look on how to use the LED matrix in the dashboard to give information to the driver or the passenger. And the last student of that group is working on a side app for the IC with more information for the driver. And the implementation starts now. The second group works on the interaction with the car, and for that we want to develop personalized interactions with the car. So we would use the user profile of AGL and the user identification, and then the user could create special gestures or could customize the car for him. And also this implementation starts now. That a student could work at the moment at home. I'm doing some side work and set up the development environments for the students to work at home. We will do that with AGL VMs and our lab software, PySim Tucan and so on in a second VM. To communicate between our software and the AGL, we will use Cannelloni to send the CAN data through AGL from AGL to our software and backwards. So we can drive a driving simulator, generate CAN messages and send them to AGL and get the values in AGL to control the applications with that. The vision that we have is that we want to build up a development environment where students could create ideas and building prototypes for any area of future mobility and do really fast prototypes. We could do feasibility students, implement and test, and do user experience development. The next steps we are doing for that vision is to finish the CAN pipeline, extend our mobile development station, that we can use it as a base for further work with textile and design as well as engineering, and do some prototyping showing what AGL could do and how we could use that to do cool stuff at university. And then we will start to do example implementation of new concepts. It should be something like the platform for Reutlingen future mobility based on AGL. When we started 2 or 3 years ago, and choose software that we could use for the interaction between the driver and the car, we made research and we found out AGL is a cool project because the openness give us the possibility to work on all parts of the system. We have the open source license, we have a great community, we had a lot of help the last years, special from Jan Simon, from Lorenzo and Scott, and we have the possibility to work on HTML5 apps, so the students don't have to learn something new, we just could use that we learn at university. At the moment we have a joint project with T-Systems on automotive service topics, and we are working on some different projects with them. But we are interested in expanding our research collaborations with members of the AGL community. So we are glad if you're interested in collaborations with us, just give us information and we could talk about that. Now to my contact data. I'm Thomas Walzer. You can contact me via email or find information on futuremobility.Reutlingen University. That was my talk. Thank you very much, and then we could start with the questions.